Okay, hi everybody. My name is Ricardo Oliveira. I'm the CTO co-founder of ThousandEyes. It's good to see you guys again after a year. I see some familiar faces in the audience. It's always good. So I'm going to talk a little bit about the way we do active probing in our platform. So going a little bit into some technical details. And feel free to interrupt me if you have any questions in the middle. So active probing is a technology or a way of measuring data that has been around for several years. It's very useful, especially for availability monitoring. It's arguably the only way you can tell if a service is available or not. It's also very useful to measure things where you don't have instrumentation or you're not collecting locally data. And especially if you think of black boxes, we have the big black box in the world, which is the internet. So it can be very useful to mine data from that huge system. It's also very useful for root cause inference, especially if you have passive information collected from flows. So you see application flows, you realize there's something wrong in an application, for instance, end-to-end packet loss, but you don't know exactly in a network where the loss is occurring. And in order to get there, you can use active probing. So there's nice properties such as repeatability of the probes. You can trigger an active probe whenever you want. You don't need to wait for a user to land in your application to get some data. There's also this notion of have a consistent baseline, because you have periodic probes you can trigger, so you know what's normal and what's not normal. And the data is much cleaner than using passive collection as well. Talking about some traditional network tools, so traditionally, people have been using stuff like pings and trace routes and MTRs to measure things in networks. These tools are good enough for most of the cases, but they can have some drawbacks, including for instance, path distortion, which happens in trace route when you have ECMP. If you don't know exactly what you're doing, you just fire the default trace route probing mode, which uses UDP, and suddenly your packets are going through different routes, and you see links that don't actually exist in the route. Other issues are with ICMP. If you're, for instance, trying to measure bandwidth using ICMP packets, good luck with that. Lots of routers in the internet throttle ICMP, so you get a bandwidth that doesn't actually make sense, doesn't reflect the application bandwidth. Here is just some examples of one case where we actually use an ICMP trace route to get to a server. In this case was Bank of America. So if you just use a vanilla trace route, you get the picture on top. The probe is actually blocked after some point, so you see that red node over there. But you can compare that with the actual topology on the bottom one, which is much richer, and it actually shows you everything. And I have a couple of blog entries where I also describe more drawbacks of these tools. So what was our objective when we start looking at active probing? We realized all these tools have drawbacks. They don't actually understand the application they're supposed to represent, so they are kind of blind. So our idea was to build this framework of active probing, where the probes are actually aware of the applications that go through the network. So the packets that we use in the probing are actually indistinguishable from application traffic. So that was one of the principles. And the other idea was that we wanted these probes to actually shed light into the entire application delivery path, even if we don't have instrumentation. And therefore, that's in the wild part, that's very important. So these are three types of metrics we support, network metrics. So on the left-hand side, you see the TCP streams metrics. So that's mostly related to web applications, but it can be used for other types of applications as well that talk TCP. You see on top the packet loss and latency. Those are very important for TCP. If you have packet loss, Anywhere above 1-2%, you're about to enter a world of pain in TCP. Latency is important also, especially for pages that have lots of components, very small components. You need to do an RTT to fetch each of them, and the browsers cap the number of concurrent connections you can have at a single time. So you end up having a poor performance on the page load. PassMTU is another interesting metric. This can be lethal for V6, because if your PassMTU is not working, V6 doesn't support fragmentation except for the endpoints, and suddenly you don't know that your packets are being dropped, and you get what they call a V6 black hole. There's also some other issues with V4. So we actually support a type of test where you can do a PassMTU discovery and make sure that PassMTU is working properly. Coming to voice, so on voice we use RTP packets. Actually, João is going to cover that in next session in more detail, our entire voice capability, which is actually something new. We are in beta and we just released that about less than a month ago. But on top you have the traditional mean opinion score metric that you're probably used to see. That's a scale from 1 to 5, 1 meaning very bad voice quality, 5 meaning very good. And obviously that metric is a derived metric from other metrics like packet loss, latencies, jitters, and so on. Another one interesting is the received DSCP on the IPQoS. As you know, when you deploy voice in an enterprise network, you need to make sure you have QoS properly configured in all the devices, such that voice traffic is prioritized over other traffic. And what happens often is someone forgot to set the DSCP mappings in some router, and suddenly your voice traffic is suffering huge delays. So making sure that the packets arrive on the other end with the right DSCP, which is the IPQoS, is very important. The other type of metrics we have are pass traces, and these actually work with any type of traffic, TCP or RTP. And what we do there is collect metrics per hop, per layer 3 hop or interface. So we are able to detect forwarding or measure forwarding loss, terminal hops, link latency. We're also able to infer whenever packets go through MPLS links just by looking at ICMP time exceeded message. And the other interesting piece we can extract is the actual DSCP header of the packet when the packet gets to a certain hop, and this is important again for the voice case, because then you can tell exactly where in the path the DSCP is being mangled. So how we do this? So we build our own packet crafting library. So that's all in C++. You build that from scratch. And that supports a variety of different probes. It's very versatile. It's almost like a plugin framework, so you can build different types of probes. And right now we're mainly focused on TCP for web traffic, RTP for voice, and we also have a bandwidth estimator probe, which is pretty interesting. That one works without any server cooperation, so it basically sends a stream of TCP packets from the client to the server and measures the available bandwidth and the capacity of the path from the client to the server, and all these without requiring any instrumentation on the server. So traditionally you do this using something like iPerf, but with iPerf you need two processes running, one on client and another one in the server. Another way to do this is through ICMP and UDP, but again, that
bandwidth estimator, is that going to give me a feel for up and down bandwidth?
So it's mostly unidirectional from the client to the server. It's we don't really have a way to measure the other direction, short of.
I'm just thinking in terms of typical ISPs and whatever. Often it's your inbound bandwidth that's the constraint.
Right. Yeah. That for enterprise environments, when you have symmetric links like MPLS1 and T1s, these usually the client to server, server to client are, in terms of capacity at least, they are symmetric. If you get to more like residential internet access where you have asymmetries, then it's more challenging. We didn't find we are still looking into that, but that's a very tough problem to do without instrumentation on the other end. We can definitely measure TCP throughput if you have an HTTP object on a server and try to download that object, but that's going to give you the TCP throughput, which can be very different from a capacity or available bandwidth depending on cross traffic and so on.
You said you built your own packet crafting library. I'm just curious, why did you go that direction?
Just because of control, so we have more control over the packets, and we can actually set every bit in the packets that we want to do. And there's lots of hacking around the packets we send. We cannot just rely, for instance, on the kernel. Sometimes we need to bypass the kernel and craft like.
Well, there are some existing tools that I've used Scapy before, but there's obvious caveats to that. So it'd be nice to see a tool like that. I'm not sure if you guys are willing to put that out there, but it'd be cool. It'd be useful.
That's something I've been talking about. Yeah, we also, by the way, use Scapy a lot for point troubleshooting. That's pretty useful.
No, but yeah, I think there's a big need for that right now, just with all of the new metrics that you guys are talking about. Those tools don't address yet.
Yeah, and I'm going to get into that in the last slide, actually. So
you're not just crafting individual packets like I would do with Scapy, but you implement a TCP, but a TCP that doesn't care about loss and retransmission sometimes, and cheats for maximum throughput. Is that right?
We actually craft in the packet, including the payload and header. So IP headers, TCP headers, and payload.
Not just on a packet by packet basis, but you implemented all of TCP with tricks
for stream.
Yeah, for some types of tests, we use an hybrid. So we actually use the kernel implementation of TCP, and on top of that, we actually use our own raw packets or fabricated packets. And depending on the type of measurement you want to do.
So I can understand why you wouldn't want to use Scapy if you're doing synthetic TCP. Yeah.
Right.
Every packet depends on previous ones.
Right, Scapy is also,
sort of like a mix between Scapy and iPerf, basically. Yeah.
Yes, Scapy is also Python, which for the scale that we do stuff is not, like for the bandwidth test, we can go to 1 gigabit per second of traffic generation by using memory buffers or ring buffers in the Linux kernel, and that would be very hard to do with Python or Scapy for that matter. So I'm just going to fly over some examples of our metrics in action. This case were partially covered by Doug in a previous presentation. This is actually the Time Warner outage that you guys probably heard about. It happened, I believe, last week, which was on our end, we saw a mix of problems. There was a lot of BGP route withdrawing happening, and that created unreachability to DNS servers, and that also created reroutes in the actual path forwarding. So in this case, what we see is we have two agents on the left-hand side that have 100% packet loss. They could just, the routes are just terminating in that red circle over there. And the way we signal the loss in the nodes, we have this metric called forwarding loss. What that means is the fraction of packets that were forwarded from that interface downstream to the immediate next hop, but we didn't heard from the next hop that the packets actually got there. So usually indicates either a drop happening in the outgoing interface of the node being circled, or anywhere in the link, or actually in the incoming interface of the upstream node. So in this case, it was actually most likely in the link, and we actually see some paths terminating there, and you see the loss here is 67%. It's pretty high. This is just another example of how we can detect MPLS tunnels. So using the path trace measurement library, we are able to generate all these traces, and then we can actually tell which of the links belong to an MPLS tunnel, including all the label stuff. And there's some type of tunnels that actually don't explicitly show the label, so we do some sort of inference by looking at the TTLs that are returned. So there's some level of inference here going on. This one is an explicit tunnel because you can see the labels. So those ones are easy. Sorry?
How do you detect the MPLS tunnels? Do you talk to the routers directly, or does an agent talk to the router?
So we can tell that by looking at the return ICMP time exceeded. There's an extension that actually most of the vendors implement these days, Cisco, Juniper, and so on, that actually includes the MPLS headers in the time exceeded message. So just by looking at that, you can tell that the packet went through a tunnel.
So it's reliant on the extensions then?
Right.
Yeah, okay.
Yeah.
Thanks.
This is another example of, in this case, our bandwidth measurements. So on the top image, you can see use case of capacity planning. So we decided to do a test from one of our agents, actually in Mexico, to wikipedia.org. We got this interesting time series here. You can see the daily patterns there. The dark blue line actually is the capacity line. So you see it's close to 700 megabit per second. It's pretty stable, pretty consistent. Then you have the lighter blue line, which is the available bandwidth. And you can see that the available bandwidth actually decreases during the day periods and increases during night, which makes sense. You can actually, if you look carefully, you can see a local maximum around lunchtime when people are away from destinations. And again, all these without any instrumentation of Wikipedia. We don't have any relations with them, so we could infer all this stuff. On the lower case, we have ESPN.com. In this case, was basically we noticed we had an HTTP test to ESPN.com, and we noticed an increase in fetch time, those spikes over there, and we thought that might be related to available bandwidth, and we pull that information, and you can see that there's a sudden decrease in available bandwidth that happened during that period, which created those spikes over there. And coming back to your question, we do have a command line version of all these tools. Right now, they are only accessible to customers. We are considering opening that up, at least the packages, binary packages, and making that available for general public, because I think these can be very useful, and especially network engineers, they live off command line tools. It's actually funny because we have several instances where our customers share snapshots with their ISPs, and they just look at snapshots and say, no, we want traceroute output, black foreground and white, black background and white foreground. Yes. Okay, so we are actually making a feature for that as well. It is pretty interesting. And that's pretty much it on my side. My last slide.
So do we have any questions on this part here, on the technology?
I had a question on the probes, actually, unrelated to this. Just as devices become more open, programmable, where you can load, container on a router or switch, do you guys ever, see going down the path of trying to, have more probes right through the enterprise?
Yeah, we do have agents running on Arista switches.
Okay.
That's something we are still in development, but it's possible. For sure. Also, we're looking at the new Cisco's ISR that have iOS XE, and the possibility of installing the agent there as a container.
It looks like it should be pretty viable to install on, say, Cumulus or something like that.
Yes.
That should be pretty straightforward.
As long as it runs
Linux. Lightweight package, I'm guessing?
Yeah, it's very lightweight, and as long as it's Linux-based, it's easier.
Yeah.
If they're not Linux-based in their own custom code, if they can support containers or support, OVAs or so on, it becomes easier to install. But for the newer generation, it's definitely a lot easier to set things up. So Arista was was done without any sort of cooperation from Arista side. It was just Ricardo hacking one weekend and figuring out how to make it run, which was what it took. So
is that live in customer environment today?
it's not been production. It's not production ready yet, but we know it works by doing a few things. So it's a matter of now getting it streamlined into a customer environment. So
I was just curious, if you look at that scenario with Arista, would it still be, at the border, within that network, or do if it's a large data center, like would you see, if it's a multi-stage data center network running BGP, like would you see the agent potentially be on every switch or at certain points in the network?
I think it depends on the objective at the end of the day. For a lot of the folks right now, their primary objective is to get a first mile view of their application without having transit in question. So, the farther it is out from the data center but not on transit, they would want that. So they can get the internal view, all the internal hops. But I think it really comes down to the use cases. And one interesting thing we'll cover in the closed session is a piece of the roadmap which makes the data center deployment really interesting. And we'll go into that later.
Right.
It's coming up next year, but it's something that will interest you guys. And we'll talk about the history behind why that capability came up as well. But a lot of our roadmap is really driven by only one theme, which is we've run into a problem which we aren't able to solve. And that drives us to why we weren't able to do this and build the roadmap further. So all the layers that have come up have been for those reasons. Like BGP came up because we had a few customers where we couldn't figure out the random packet loss in different ISPs. It just didn't make sense. And then we realized there was BGP flapping going on. So we put the layer on top.